Ladies and gentlemen, welcome to this lecture on smart charging of electric vehicles. I'm Gautham Ram and I'm an assistant professor at the Delft University of Technology. In this lecture, we will talk about what is smart charging or V1G and vehicle to grid or V2G. And why do we need smart charging? Also, what are the applications and benefits of smart charging? And finally, we will talk about what are the critical challenges for the implementation of smart charging. Smart charging is a series of intelligent functionalities which enable the communication of information and services between the electric vehicle or EVs and the smart grid stakeholders to supply and maintain a safe, reliable, sustainable, and user-friendly charging environment. All these functionalities can be achieved by creating and distributing the available power, efficiently and flexibly amongst all the electric vehicles. Effectively, we can get the most out of our charging stations and the electricity grid in case of limited power capacity at any time, at any place. The key benefits of smart charging or V1G is the possibility to increase the flexibility in terms of time and power level of charging. Second, controlled charging results in a higher utilization rate of grid assets like transformers by reducing the peak demand on the grid or shifting it to moments of low demand called valley filling. This directly leads to the third benefit that better grid utilization can reduce or altogether avoid expensive grid reinforcements. Fourth, and more important from an energy transition perspective, smart charging can help increase the use of renewable energy, therefore making electrified transportation 100% sustainable. And lastly, smart charging provides new revenue streams to the EV owners from participation in ancillary services such as frequency regulation. Let's first look at how charging of electric vehicles is done today. If we have multiple electric vehicles arriving at a charging station around the same time for charging, then the charging process will start immediately for all the vehicles and the charging powers of the EVs will add up one on top of the other since the charging happens simultaneously. This is referred to as uncontrolled charging and it creates a peak demand on the electricity grid. On the other hand, if you factor in when the vehicles must leave and how much energy demand they need, then the charging can be intelligently spread out throughout the day as shown. In this case, cars 1, cars 2 and cars 3 charge one after the other instead of all of them charging simultaneously and creating a peak. By doing this, the peak power demand on the grid is drastically reduced compared to uncontrolled charging. Do recognize that in both the cases, the uncontrolled charging and smart charging, the total energy demand is the same. It is the power demand and the peak power demand that is different. To implement smart charging, we can use 4 degrees of freedom. The first is to control the magnitude of charging power as a function of time. Do you want to charge at 1 kilowatt or do you want to charge at 5 kilowatts? The second is time flexibility to design when to charge the vehicle and when not to charge the vehicle. The third one is charging direction. Smart charging can be both unidirectional and bidirectional. With vehicle-to-grid technology, you can not only charge the vehicle but also feed the energy stored in the vehicle battery back to the grid. And lastly, the fourth degree of freedom is ramp rates. Electric vehicles have fast ramping rates, so the charging power magnitude can be changed from one value to another in the order of milliseconds. With our understanding of smart charging, let us now look at specific applications and their benefits. The first application of smart charging is to control the charging of the power based on the renewable energy production, like solar or wind. This will ensure the optimal use of renewable power and make electric vehicles 100% sustainable. With vehicle to grid, electric cars can also be used as a massive energy storage to balance the variations in the renewable energy sources. Second, smart charging can help with congestion management in the grid by shifting the charging time or adjusting the charging power based on the grid capacity and local loading conditions. For example, when the load on the grid is low, the EV charging power can be increased. Subsequently, when the load power increases, the EV charging power can be reduced. Finally, the EV charging can be stopped if the grid is overloaded and remain so until the grid demand is back to normal. Another example is when there is a limited maximum power for charging cars. Smart charging can then be used to operate multiple charging points sequentially based on priorities, or adjust the powers of each charging point to be within a maximum limit, or each car can also be charged with different strategies according to the load and the priority. Besides smart charging, vehicle to grid can play an even more prominent role in congestion management, and the vehicle can act as a local power generator and provide power at the moments of grid congestions to achieve peak shaving. In this example, the EVs can be charged when there is extra renewable energy generation in the afternoon, and they can discharge via vehicle to grid at a point when the peak load is in the evening. Next, we look at price-based smart charging. Here, the charging power is increased when the electricity prices is low, and the charging power is decreased when, or even stopped when the electricity price is high. Effectively, you reduce the charging cost for the user. In addition, customers can get more profit when vehicle to grid or V2G is applied. For example, we can charge the cars when the electricity is cheap and discharge the car and sell the energy to the grid when electricity is expensive. And finally, smart charging can also be used for frequency regulation, where the electric vehicle power is continuously adjusted to maintain a balance between supply and demand of electrical power in the grid. In case of frequency containment reserve, or FCR, response is needed within 30 seconds, which can fortunately be very easily met by electric vehicle batteries because they can respond in the order of milliseconds due to the fast ramp rates. Despite all these benefits of smart charging, there are still a few key challenges. First, market mechanisms at the distribution system operator or DSO level are needed to incentivize congestion management. Second, net metering reduces the incentive to store and increase the self-consumption of energy via energy storage or EV batteries. Third, regulation for FCR or frequency control reserves have a minimum bid and a delivery period which requires a large number of electric vehicles in order to participate. Related to this is that we are yet to build the digital infrastructure for aggregating and coordinating millions of geographically distributed EVs. So, to summarize this lecture, we first defined smart charging and vehicle to grid and looked at the 4 degrees of freedom, namely power, time, direction, and ramp rates. We looked at various applications of smart chargings like charging from renewables, congestion management, and price-based charging. And lastly, we looked at some of the key challenges to implement smart charging. Thank you for listening.